All right. Hi, everybody. I'll start off, set some context for the talk. First, we'll do some introductions. Obviously, I want to know more about you all to make sure that I cover the things that you all care about. And then I'll talk about 5 different ways to process data using Spark and Python. There are probably a couple other ones, but I gotta cut it down somehow. And then we'll talk about 2 data science use cases at Databricks and sort of how we've gone about implementing them, and really focusing on the high-level lessons that you could take back and apply at your own company. So we'll start off with data scientists, if you could raise your hands. Okay, now data engineers. Okay, good combination. And then years with Spark. How about let's start off with 1 year or less. Good times. 3 years. And 5 years. Okay, cool. And then Spark Summits. 1. Okay. 3. Okay, 5. I have 5. And then Catalyst Optimizer. When I say that, raise your hand if you know what I'm talking about. Okay, good, great. And then years with Pandas, 1. Okay, so not 3? 5? Okay, so not a ton of familiarity, that's totally fine. And then we'll talk about sort of models or data science use cases in production. What about 1 or less? How about that? Well, let's start with 0, I guess. Okay, order 10, order 100. Okay, cool, work to be done. Great, so quickly, because naturally I want to cover a lot here. So I've been at Databricks for about 4 years now. Started off as a solutions architect, then I spent a couple years in product management, making a mess there, and then now I'm in data science and basically helping to implement, how we can do a better job understanding our customers. Because at Databricks, being customer focused is really, really important. So I was also fortunate enough to work on a book on Spark. I learned a ton doing that. We put a lot of effort into this book, and it'd be awesome if you want to get it. On top of that, I have a master's in information systems from Berkeley, and I was originally a history undergrad. So it's been a long way to start talking about big data. And so I think it's also important to talk about my biases, right? And I think that Spark in general is an awesome tool. I mean, wrote a book on it, so I better think it's good. And then from a principles perspective, I think really being organized in your thinking and your approach to problems is a really, really important key to success, and that comes from a master's degree. And I think lastly, I have a big bias for really practicality and a bias for action. And that comes from the history grad, because I don't have the theoretical foundation, so I have to poke and prod and figure out what works and do it the wrong way 80,000 times before I get it right. Cool, so let's move right along. And so let's talk about the 5 different ways of processing data with Spark and Python. So here are the 5 ways. We have RDDs, DataFrames, Koalas UDFs, and Pandas UDFs. So I'll go through each of these and kind of give you that high level, hey, what's actually going on here? So resilient distributed datasets, or RDDs, was or continues to be the sort of core abstraction of Spark. And here's like a little code sample. Here's kind of what you get back. So the principle of RDDs is that you're working and manipulating raw objects. So I could parallelize a range of integers like I've done in this example, or you could do even Python classes or objects or whatever it may be. And when it comes time to actually computing with RDDs, that actually requires a ton of work. So you start off, we'll move left to right. You start off in the JVM. You need to serialize that row of data, which just means convert it into a format that you can interchange into another language. Then Python has to change it back into whatever Python understands. Then you perform your operation, and then you do the reverse. And that has to happen for every single row on the cluster of machines that you're working on. And so that ends up being really expensive to do computationally, just because you're doing a lot of work that isn't associated with the problem you want to be solving, right? So they're pretty expensive to operate. You're starting and shutting down processes. You have to start up that Python process on the worker every time. And you've got serialization and stuff like that. A lot of some of the problems that Gail was talking about. Also, the majority of operations when it comes to RDDs can just be done with DataFrames, and you'll see why DataFrames are better momentarily. And so really you shouldn't use RDDs with Python. It's more of a historical artifact with respect to Python than anything else. So definitely don't start here, especially as you're early in your Spark journey. You're just going to be upset. So DataFrames. DataFrames are really the sort of key abstraction. They're really the fundamental abstraction in Spark nowadays. And they share similarities with Pandas, which of course you guys aren't really that familiar with, so that's probably not the best example, but they're really similar to SQL tables, right? So you can operate on them with SQL or by performing, a variety of data frame operations. And the way data frames really work is you'll notice, when I printed out the output from those print statements, you'll see that it says row ID equals 0, and then row ID equals 1, and column 2 is equal to 10. And all that is really communicating to you is that there is this row object, which has special properties, which we'll talk about in a moment, that is now materialized. And obviously that differs from RDDs, which are just the raw objects. And so basically the way DataFrames work is Spark has this internal row representation that's it was called Catalyst. And that was written by Michael Armbrust, who did the sort of emceeing, if you will, yesterday. And essentially what it is it's just an encoded way of representing whatever is inside of that data, assuming you're using sort of strings or integers or whatever it is. And what that really allows you to do is that if you remember that cost of like serializing objects or information, what it allows you to do is just operate on these raw bytes whenever you can. And that means that basically stability is really improved because we can understand the performance characteristics of doing that rather than working with sort of arbitrary collections of information that you as a user would provide. And on top of that, it makes it really efficient to sort of exchange around. And so whenever you're doing an operation there, it's really just manipulating that internal row. And so that's going to give you really big stability improvements, and it's going to do it a lot faster, and naturally it's a lot simpler too. So really, DataFrames are going to be where you want to start. They're going to provide basically operations for most anything, certainly anything that you could find in SQL. And then by using this internal format, DataFrames actually give Python the same performance profile as Scala, and so or Java. And so that's a huge benefit as a Python user. So that's sort of what brings us to Koalas DataFrames. So the big gripe, if you will, is that the DataFrame syntax for Python and PySpark and so on has its own flavor, right? Just like everything else. And so the Pandas library, which is a popular sort of single node data manipulation library, is quite popular. And so Koalas basically seeks to imitate the Pandas semantics, if you will, and put it on top of Spark. And that's really all that it is. There's like not really much else to Koalas. And so along those same lines, it can make things simpler if you're used to working with Pandas, but if you're not, then you're not going to really get anything out of it. And so what you'll get at the end of the day is really just that same data frame transformation that we had just sort of spoken about. It just behaves slightly, or rather it just has an interface that's slightly different. So it's something that if you're really familiar with Pandas, then Koalas can give you some API consistency, but it's never going to be fully either one. And so it's kind of a mutt in that way, but it has a lot of power if that's something that you're familiar with. And so try it and see if it covers your use case. And then if not, just getting familiar with DataFrames is not going to be bad. But I think the key gap that sort of comes up with RDDs and DataFrames is that really there's no way to run custom code. Remember I was saying you can't use generic objects with DataFrames, at least yet. And so there's no way to run this custom operation that you might want to code up in Python. Maybe it's something really, really particular. Maybe it's a date manipulation or really something crazy that would be difficult to do in raw SQL. And so these next two sort of transforming or Python-based methods are really user-defined functions where you'll define them and then Spark will take care of running them for you. So DataFrame UDF basically follows, there's a sort of trivial example here. So we create a data frame. We're going to import this UDF function, and we'll use it as a decorator to create basically this Python function that we can then use as we would a regular SQL function and operate on that second column. So this will give us that column 3 UDF, obviously the value just multiplied by 10. And what that really ends up requiring is a lot of those same basic RDD hops. It's really no different from an RDD, except that maybe there's even more serialization here. And so the kind of key point is, I think calling these legacy Python UDFs is pretty fair, and they're really just RDDs. And they suffer from nearly all the same inadequacies, except that maybe you can do some of your manipulations with DataFrames and then really only drop down to Python where you need to. And in general, these should never really be used in place of Pandas UDFs, which we'll talk about in a minute. So at this point, we've kind of covered a couple of different use cases, right? So we started off kind of talking about these legacy RDDs, which are still sort of important in the Scala world, but definitely not relevant in Python. And we talked about DataFrames, and so now we're talking about the next generation of UDFs and running your own user-defined code. And these are Pandas UDFs. And so the reason why Pandas is so popular is that it's a really optimized and great tool to use for single node data manipulation. A couple of years ago, I actually created like a class on Udemy that you could probably find on the internet that walks you through how to do basic stuff with Pandas. But really, for all intents and purposes, it's a really efficient data manipulation tool for single node sort of operations. And all this UDF allows you to do is create these functions. You can test them right there on your local machine and then perform them at scale. And I think a really nice differentiator here is that you can do it on an individual row, or you can do it on multiple rows. And we'll see why that's important in just a little bit. On top of that, there's some nice optimizations. You still have to do this whole serialization, deserialization, hops, and so on and so forth. But it piggybacks on this project called Apache Arrow, which is basically like a shared in-memory data format that allows for more efficient transferring of data, like rows of data between different languages. Kind of like how we were talking about Catalyst has that internal representation that's defined just for Spark. This is one that aims to bridge different languages. And so by using Arrow, it can turn this into a Pandas UDF with much less hops, as it were, than if you were using a regular UDF or an RDD. And then the operation that you're going to be performing, it's no secret that Python isn't necessarily the most performant, but by leveraging Pandas and NumPy and stuff like that, you're going to get a much better performance profile for those individual operations as well. And so what's really nice is that it's very flexible, kind of follows best practices. The performance won't match pure data frames, so like don't it's worth it to benchmark it to understand, hey, kind of what you're actually working with, but I wouldn't go in with the expectation that it'll match. And the limitations are going to be pretty challenging. I mean, it's not so much the sort of working with this particular UDF itself, but whenever you're hooking up lots of different machines or different hardware, you're going to be challenged figuring out all of these particular configurations. And so obviously that's something we're working on a lot at Databricks, just trying to make that a little bit easier. And then lastly, whenever you're performing this sort of using a Pandas UDF, you're going to configure this thing called a batch size. And all that means is, all that specifies is when you're taking a chunk of information from basically Spark itself, and you want to transfer that into Python to be operated on, then you're going to need to specify how many rows you want to do in a particular chunk, if you will. And so this batch size means that that entire chunk of data will end up inside of the Python process. And so you're going to have to fit that whole thing into memory. And so if you're trying to do an operation on a huge, billion rows, that's not going to work, and it's going to crash. And so there's largely the survey of all of the different kind of methods that you can leverage to take Python code that you have and run it using Spark. And given those basics, I think the really key conclusions here are that, if you want to, use Koalas if it works for you, but Spark DataFrames are sort of the safest option. And Pandas UDFs are great for user-defined functions, and I think that's kind of the long and short of it for today. And so next I'll talk about these two data science use cases. We'll do sort of like a little code review of how we went about doing it, and kind of how in particular we leverage Pandas UDFs to approach the problem that Gail was talking about, which is sort of data parallel problems or model parallel problems. So with that, the kind of use cases that we were focusing on is that really we were looking at churn prediction and growth forecasting. So pretty simple use cases. I think they're great illustrations of how best to kind of use these. And in terms of growth forecasting, there's kind of two different methods, if you will, or two different flavors. You might want to only use the information about, say, a single customer or a single user. And so that's, I'll get to sort of low N, K, and M in a moment. Or you're going to want to use information about all your customers, which means, might be much bigger data that you couldn't operate on an individual basis. And then churn prediction overall is, I guess we don't have very much churn, so there isn't too much data there. And so we end up just focusing a lot more on actually model tuning and really trying to solve that problem correctly. And so those three key dimensions of sort of N, K, and M, or N, P, and M, whatever you might want to call them, is really like how many input rows are you going to have to this particular model, how many input features are you dealing with, and then how many models you actually need to produce. So in some problems, for example, for that churn prediction problem, you're really only producing one model, which is, hey, will this customer churn? But things get a lot more complex when you want to basically create a model for lots of individual customers. And so there was a presentation by TomTom yesterday, and they did a great sort of overview of using information about a single customer to try and predict where that customer would drive next. So they're sort of a mapping company. And I think that's a great talk too. If that's a problem that you're trying to solve, I would recommend that you check that out. But so really our focus ended up being on this sort of producing lots of models individualized for particular customers. And so the historical approach for like how you would go about solving that problem is that Spark, the Spark cluster itself has a driver. The driver is sort of where you actually input your commands, and then there are the workers or executors, which are all the nodes that will actually operate on the work, and so or on the data. And so typically what you would do is you would say, hey, give me all the data about all my customers if you're using Spark to maybe do some aggregations or pre-processing. And then you want to iterate maybe over every customer. So you like collect a chunk of data for about a customer. You would then train a model on it, store the model information there, and then rinse and repeat for every single user or company. And that is a very expensive process because it's just going to take a lot of time, right? There's just a lot of processing, data exchange, so on and so forth. A maybe more advanced historical method, which probably isn't too relevant for this audience, but it might come up in another context, is that the RDDs, or resilient distributed data sets, have a method called pipe, which allows you to basically pipe some data to another process on the workers. And so where this is frequently used is, let's say you have like a C++ model or whatever it may be, something very, very high performance, then you would actually take some data and pipe it to that particular process or program on the executor machines, and then be able to do things in parallel that way. I wouldn't really recommend it unless that's something like you really need to solve. And I can point you to some resources if that's something you need to do. And so our approach here is really just use the Pandas UDF for distributed training of small models, and we'll sort of do a code review of that momentarily. On top of that, let's say that you're actually trying to look at all of user information and really be able to make predictions that way. Say you're trying to do a forecast and you want to try and leverage information about all other customers to maybe make a forecast about a customer that doesn't have as much usage, something like that. That's where you're really going to want to default to using Spark's MLlib. Or if you really want to try and get fancy, you can use something like Horovod, which is a basically way of training neural networks in a distributed manner. I wouldn't really recommend that be your place to start, obviously, but hey, you can make we're all grown-ups here, so you can make your own decisions. Cool, so then we'll talk about churn prediction here. So again, you'll notice like the theme of Pandas UDFs, which is really what I'm trying to evangelize here. And really the historical approach would be that you would maybe tune a model on a particular machine, right? There's really not even necessarily a need to kind of use Spark in this context, because you could just run it on your local machine. And it basically ends up being, in general, a much more complex process to try and distribute training and do grid search. You can play around with SSH and SCP and copy lots of files and models around and stuff like that. But you'll kind of see in a moment why that ends up being much more challenging than one might hope. And so our approach here is going to be use this Pandas UDF for distributed hyperparameter tuning of really small models, and really just using every tool for what it's kind of best for, right? So with that, you can find the code in this GitHub gist. But what I will do is I'll just go ahead and jump through here. Okay. Awesome. So I will just go ahead and take you all through these different chunks of code. This whole notebook is just on the gist, so it's pretty easy to just go through and play around with yourself. So RDDs, right? Talked about those being the sort of core primitive. Here's me just running that code, taking a look at those first couple of rows. Here's where you can see that actual sort of encoding format of row IDs and so on and so forth. Here's Koalas, basically the same kind of thing. You're going to see a lot of similarities kind of between these. Obviously, we're just operating on a distributed collection of data. And here's where things get a little bit more interesting. Here we are working with a regular UDF, operating on that. Here is the Pandas UDF. So one sort of catch here, if you will, is that the inputs and outputs have to be of Pandas data types. So it has to be a Pandas series or a data frame. A series is just a single column or row, depending on your perspective. And then a data frame is obviously multiple. Great. So now, let's see. I don't think I have. Yeah, great. So now here's the distributed model training. So this is basically just a really toy example. I've taken this little basic data set here. I renamed the columns so that it make a little bit more sense in our kind of context. It's kind of a small data set, but what's really nice is you can turn around and just run this on your own machine or on Databricks if you like. So basically what I do here is I have an imitation of the data set that we'll kind of be working with. We have a couple of different feature rows. we have a target variable, and then we have a customer if we're going to do a particular customer prediction. And so what I do here is I have a simple sort of train model function. And this will take in the raw data set. I'm not doing a train test split in this example, just because I want to try and keep the code as simple to follow, so you can just manipulate this to however it fits your use case. And we'll train a linear regression model. So I'll drop the customer. So this is the this is training lots of kind of small models here. So I want to drop that customer one because each of these will be an individual model for an individual customer. And print out the coefficients and return basically a success or failure. So there's the example of using it on kind of a single node. And here's me creating a Pandas UDF. So I'm no longer using it as a kind of decorator. I'm simply passing in my function so that I can distribute it. I have to specify essentially the return type. I have to keep these really simple because you're going to end up wanting to manipulate it, or you're going to want to, basically it's keeping the API really quite narrow. And if you specify a really complex kind of return data frame, it's going to be really hard to maintain going forward. And I'm specifying this as a certain type of operation, which is a grouped map. So what I'm able to do here, let's see, go ahead and run all these. So what I'm able to do here is Spark will take this particular Pandas UDF and it'll apply it to every group of customers in this particular data set. So I think I created, like 15 different customers. And so this will have probably, it should have 15 rows, assuming the randomness makes sense. And it'll train a given model for that customer on every node in my cluster. And so that makes it really, really efficient to train a lot of models really, really quickly. That's been really, really valuable for us to basically speed up the way we can kind of iterate. What's also nice too, as you'll kind of see in this next example, is you can actually couple that with hyperparameter tuning too. So in this next example, I'll be doing a single, basically I'll have a single small data set. And it's actually the same data set that we used. And I will train basically a collection of models using all the nodes in the cluster as well. And basically this time, I'm taking the data from the driver machine and I distribute it to all the workers so that they can operate on that same chunk of data. And so here is a little bit more sophisticated of an example. I have basically like a simple, this is all in sci-kit learn. I have a simple preprocessing here where I do some scaling. Then I have a linear regression. And I actually have multiple models here. So here's a linear regression, and then I run a ridge regression as well. And I set the parameters that I want to tune. And so along those lines, you'll see here that I create really the same kind of structured function where I'll have the pipeline. So I'm using the sci-kit learn pipeline interface. I guess, is everyone familiar? Let's do the 1 through 5 on sci-kit learn. So 1 year of, or 0 years of sci-kit learn. Okay, 3? Okay, 5? Okay, got it. I'll just take a step back and do a little bit more introduction of sci-kit learn. It's a great single node library for doing machine learning tasks in Python. And it has some great organizational structures. Remember I talked about my biases here. For basically creating a collection of operations that you want to operate on that sort of raw piece of data. And what's really nice here is that by using this pipelines interface, I can couple my pre-processing as a hyperparameter in addition to just like the model typical hyperparameters. And so what's really nice here is that it'll train for this, for instance, for this first model, it'll train 4 models and then obviously return whichever one is best, or I guess I could get the worst one if I wanted to. Great, so I'm using this pipelines interface. And you'll notice too that I don't really have to do anything fancy here. It's going to go into this models list and collect the first one. So the way I do that right here is you can see I'm using the index, which will come up in a moment here, because basically what I do is when I pass in the value that I pass in to my Pandas function is actually just the index of which model I want to train. So if I pass in 0, like I do here, I'm basically specify this model, or train this model at 0. And if I specify 1, it would train the next one, and so on and so forth. And then here I actually do grid search on that individual machine for that particular model. So the grid search down here in this function actually just applies to this first model right here. And it'll fit it, and it'll, I was sort of playing around with it, so I sort of removed my try except statement. But yeah, it'll go through and train it that way. And so I create this Pandas UDF. I specify that it'll return a long value. And then basically what I do here is I simply distribute a range of the number of models that I have, so every index value. And then I just pass in that index value to the model training UDF right here, and then the training result will return. So if it's success, it gives me 0. If it's not, it'll give me a 1. And this is really nice because you can just do a lot of hyperparameter tuning really, really quickly, really, really efficiently, and frankly, it's not very complicated to do. I think that's really the big value add here, is that you're pretty much going to have to do this on your individual machine anyways, and so now you can just do it a lot faster. So lastly, I guess I'm kind of giving up the punchline here, but the final gap is, well, I guess it's worth repeating that each of these methods basically operates slightly differently, but fundamentally we're either distributing the data and then training a model on a subset of the data or the entire data set. And I think really, obviously a big focus here is that you really want to be consistent when you're producing these models, right? Especially for those of you that are maybe like the 5 or 10 kind of models, you're like kind of figuring out that, hey, here are the things that I need to track consistently, otherwise I'm going to get myself into trouble. And what was really driving me nuts through the process of working on some of these use cases is there's sometimes you see like particular behavior or something seems too good to be true, and you go to, you say to yourself like, hey, how can I go about repeating that, right? And this comes up even worse in the team context where, if someone on your team has a really good result, but then you can't actually reproduce it, then it's pretty useless at that point. And so the way we approach this problem, obviously there's like a lot of talk about MLflow today, and I think really the simplest part, or the way in which we're really using it internally at this point is really for really simple tracking of all inputs and models and results and so on and so forth. And what's really nice is that you can just rebuild everything from scratch if you need to. And so it's really great for debugging, making sure that you have the correct features, for comparing models that do wildly different, maybe have the same output, but do it in a wildly different way, and so on. And so with that, I'll just jump to the example here. And you'll see that it's more or less the same basic pipeline here, except now I've specified that I'm going to create an experiment here. That'll show up inside of my workspace here, which I'll demonstrate in a minute. And now I've created this train model here. So going down, we see that we grab the model from the index, grab the hyperparameters that we want to try out. You'll notice that I specify a model type that comes from that pipeline itself. Then I perform the grid search. I'm going to grab the training mean squared error. And then you'll notice here at the end that I record all of those values. And what's really nice about this is where I've seen people have a lot of challenge is, you do the Pandas UDF, great. You start distributing it around, and that's where the complexity really crops up, because now you want to return the training mean squared error or some other accuracy metric. Maybe you want to return some collection of the data or whatever it might be, and you end up sort of really overloading this function to do a lot more than you really originally intended. And so, from a very high level, you could really imitate the value that MLflow is providing here by standing up a database and really just logging lots of metrics to that particular database. But what's really nice about doing it this way is that I can use this on a single node on my machine, or I can use it on one of the worker nodes. And in doing so, all of that information will then show up in MLflow so that I can actually compare the mean squared error or the hyperparameters or whatnot. And while I don't demonstrate it here, just sort of keep things simple, what's really nice too is, here I've actually saved the models themselves, including the untrained version as well as the trained version. And what's really great about doing that is you can go, and if you need to debug something or if you've implemented something in a custom way, these are really, really helpful for actually going back and being able to reproduce everything. And I really haven't had to do that much work to really be able to leverage this. And I sort of whipped together this notebook in just like an hour or two, simply because I know, hey, this information will show up here, and I'll have to think about connecting some esoteric system and so on and so forth. And so, I think that's kind of a big value add there, just for keeping your own sanity as a data scientist. I think there's enough trouble. There are enough challenges simply trying to clean the data that you're working with to actually solve your problem, that managing basically the data exhaust, if you will, from the process and whatnot, you might as well just make it really easy on yourself. And so with that is my talk, and I'd love to take a couple questions.
Okay, we have time for 1 or 2 questions. If you have a question, please raise your hand and I'll bring the microphone to you.
Thanks for the talk. I have a question regarding MLflow and its use when you're training for, let's say, thousands of users, so a model per user. Can MLflow easily allow you to assess like more than several factors of magnitude of models across your customer base?
Yeah, that's a good question. You mean, I guess in what way? In what kind of assessment?
So in the sense of you have one model for customer A, and that has a root mean squared of, I don't know, some arbitrary value. And then the next model has something that performs worse and another one that performs better. And you want to see how your overall system perhaps performs across your whole user base.
Yeah, that's a great question. I think where the big benefit that we kind of derive is you figure out which models actually end up kind of making sense. Because what you can end up with is, if you're training a bunch of different models and so on and so forth, you could end up with, if you train, if you have 100 customers, you train 100 models, you could end up with 100 different models for every customer, where one's like a neural network, the other one's like a random forest or whatever it might be. And it's kind of a tool in helping to kind of manage complexity and manage overfitting that way, right? Because our end goal isn't to like build the best model for an end user, it's to basically build something that's gonna generalize well. And so along those same lines, I think where the big benefit is more of just having really the disciplined tracking of it allows you to pick up where like another user kind of left off, or one of your coworkers, kind of left off, and know where you're at and know where you'll be able to reproduce it. And in terms of like large scale analysis of these different models and so on and so forth, MLflow itself doesn't necessarily provide that much value at this point, but simply by logging it, that's kind of where we're capturing it.
Okay, thanks.
Yeah.
One more question?
Cool. I'll be right outside too if there are any other questions.
So don't forget to rate this session in our app, and let's give another round of applause for Bill.